Okay, we are now going to figure out the antiderivative of tangent. We haven't done this before. We don't know any function when we take as derivative that spits out tangent. But we're going to do this using integration by substitution. First, I'm going to write tangent as sine over cosine. Now, I'm going to do this wrong at first, because this is, like, I remember when I first learned this, this is what I would have tried. You might try u equals sine of theta, because then du is cosine of theta, d theta, and you might think, oh, okay, yeah, I'm going to get it. But I do not have du in front of me. That cosine's in a denominator. Think of it like this. That d theta is on top. Cosine's in the denominator. I need to have this exactly perfectly cosine times d theta sitting in front of me, and I don't have that. That's d theta divided by cosine. So this ain't gonna work. That says nope. Looks like nor. No, didn't work. So maybe we try u equals cosine of theta, the denominator. Then what's his derivative? It's negative sine of theta, d theta. Do I have du sitting in front of me? Almost. I've got sine times d theta. I don't have a negative, so here, let's put a negative in. And I can do that by also multiplying outside by negative. That worked. Then this entire top with that negative will be my du, and the bottom will be u. So that negative there comes along for the ride. I'll have du over u, or we could also write that, I think it'll be clearer if I write that as 1 over u du. I know the antiderivative of 1 over u. It is the natural log of the absolute value of u plus c. What is u, though? Remember our final answer, we got to use the same variable we started with. Our final answer then, u was cosine of theta. And we could stop there. I'm not going to. Like, there's our answer. But I'm going to use some rules of logs here. I could write that as natural log of the absolute value of cosine to the -1 power. Well, that would be 1 over cosine, right? So I brought this negative in, made it an exponent. 1 over cosine is secant. So the antiderivative of tangent of theta d theta is the natural log of the absolute value of secant of theta plus c. Okay, let's do another one. Okay, so I've got something. When you're doing u sub, if you see something in parentheses, that's probably your first guess for doing your u. See, I've got something in parentheses raised to a power. Let's try u equals natural log of x as our u sub. Then what's the derivative? We know this. The derivative of natural log of x is 1 over x dx. Don't forget your dx there. Then right there, 1 over x, like put 1 there for 1 over x dx. There's my du. And then this guy will be u. It's always 2 substitutions you're making, your u and your du. So u to the 5th du. 1 over x dx, all that is now gone now, replaced, substituted with du. And that guy right there was u. I know the antiderivative of u to the 5th is u to the 6th over 6 plus c. But what was u? Natural log of x. So I will get natural log of x to the 6th power over 6 plus c. Check this on your own. Take the derivative of this. See if you get ln of x to the 5th over x. You will. Let's do some more. This guy here, if I had this, you'll see this in calculus too. I could give you the rest of your life. You will never find the antiderivative of e to the x squared dx. It does not exist in terms of elementary functions. This can be written down using power series, but that's an infinite series of functions. It's much easier to take derivatives than it is to take antiderivatives. This guy does not have a simple elementary antiderivative that you can write down in a finite number of steps. This is a different problem. I've got e to the x squared times some extra stuff here. So maybe we'll think of, maybe you might try u equals maybe this. Let's try it, and it's not going to work. Then du would be the derivative of e to the anything is e to that same thing times the derivative of what's up top. So if I tried to call this thing u, so that would be gone, that would be u. This, what's left over, is not du, because I've already used that guy up. He's gone, he's already u. This wouldn't work. I don't have two of these floating around in there. So that would be your first thought to try, and it doesn't work. Let's try instead. If you got something in an exponent, that's a good thing to try for u. So just the x squared. Then du would be 2x dx. Do I have that sitting right in front of me? Almost. I've got a 5 instead of a 2, but I can fix that. I'm going to pull that 5 out because it's just in my way. I wish I had a 2 sitting right here because you have to have du perfectly in front of you. Well, I'm just going to put a 2 in. I'm allowed to do that as long as I also cancel that 2 out. So here's du, all of that stuff. That's my du. And the exponent right there, that's u. So make those substitutions. I'll have e to the u, x squared was u. 2x dx was du. I know that guy's antiderivative. Antiderivative of e to the u is e to the u plus c. What was u? It was x squared. How would I check this? Take the derivative of this, see if you get this back. Okay, and maybe for fun, we'll do the same problem using that solve for dx method that some students like. It's the exact same problem. U equals x squared. Du would be 2x dx. Solve this for dx. Dx then would be du over 2x. Now I have to substitute this and this in and rewrite everything else that I see. So I replaced dx with du over 2x. I replaced x squared with u. Now, like the way this looks right now, this is impossible to do. You cannot do an integral with two different variables floating around. Oh, but luckily, all those x's canceled out, and you get 5/2 antiderivative of e to the u du, which we're right back where we started. Again, some students like this method of solve for dx. I think a better method is figure out what du is, and then make sure you got that perfectly, exactly the way it looks sitting in front of you. You can't add in extra variables to get it. You can't add in extra numbers, but you can multiply in extra numbers to get a number that's missing. Say the 2 was missing, so I put in a 2 and took out a 2. Okay, one more, and then we'll get to definite integrals. That'll be a separate video. Okay, if you've got a fraction, a good thing to try, like this happens a lot, is the entire denominator. Let u be the entire denominator. See what happens. It might not work. I might be wasting my time right now. I'm not, it's going to work, but we don't know. Then the derivative of that. What's the derivative with respect to x of e to the x? Derivative of 3 is just 0 dx. So the bottom is u. All of that I called u. Hey, look, there's du right there, already sitting in front of me. So this would be the antiderivative. This is 1 over u du. That's my du. I know that guy's antiderivative. That's natural log of the absolute value of u plus c. But what was u? E to the x plus 3 plus c. There's my antiderivative. Okay, that's a good place to stop there.